Hello everyone, this is Dr. Lennon, and in this video we're going to talk about polar coordinates. So let's just recall the old system that we use is the Cartesian system or rectangular system. So in this system you have horizontal component, the x component, and the y component defining every single point in the plane. So if you have a particular point, it's defined by its horizontal distance from the origin and also its vertical distance, the y component. Now this isn't the only way to, so this is the Cartesian or rectangular method of identifying points in the plane. There's another method, and this method is the polar coordinate method. And essentially what it does is it thinks about each point in the plane based on two things, based on a distance from the origin. So if you have a particular point, you can actually think about its distance from the origin, and then also the angle it makes to the nearest positive branch of the x-axis. So what happens is you get this fixed distance r, and you get this angle, again, counterclockwise is the orientation. So you can define each point in the plane by an r and a theta. And you can think of those distances as being just a bunch of concentric circles about the origin that would represent each point. So one of the first things you want to talk about is how can we convert between Cartesian to polar and vice versa. So let's go ahead and do an example of such a thing. Essentially, it's going to come down to two things. So maybe I'll talk about how the conversion process works. So converting coordinates. So the first thing, if we're going from polar to Cartesian, it's pretty easy to think about how to recover the 2 points, because if you have some, say, an r and a theta like we had before, what we want to do is we want to recover the horizontal component and also the vertical one. So if this is r and this is theta, we know the component is going to be essentially just the radius times the cosine of that angle. So your x-coordinate in rectangular is going to be r times the cosine of theta, and y is just going to be r times the sine of theta. Pretty straightforward. So what about going from Cartesian to polar? Well, on the one hand, if we have an x and a y, no matter where it is, we're trying to essentially just find the hypotenuse of a right triangle, right? This is going to be our x, this is going to be our y, and if we want to find r, we have a right triangle, so we can just use the Pythagorean theorem. So we know x squared plus y squared must equal r squared. What about theta? Well, it's going to depend a bit on which quadrant we're in, because in general, right, the principal value region of the tangent, the inverse tangent function, is only going to be pi over 2. It's not going to be the full, or it's the principal value region has distance pi. So what we're just going to write down here is where we're going to write down the tangent of theta is equal to y over x. And if you know, when you're actually doing conversions, if you know x and y, you're going to know which quadrant that your point is in, and that's going to allow you to figure out what theta is. So it may give you the correct value of theta, or you may actually have to add pi to that value depending on which quadrant you're in. So let's go ahead and look at some actual numbers where we can do the converting. Let's get some actual points and do the practice that way. So example, let's go ahead and, so for part A, we will convert the 0.2, 3 pi over 4 from polar to Cartesian. Okay, so again, we just use the formula above. There's not too much to think about here. X is going to be 2 times the cosine of 3 pi over 4. Again, we know that's in quadrant 2, so that's going to come out to negative radical 2 over 2, and multiplying by 2 cancels the 2 in the denominator, so we get negative square root of 2 for the cosine, and y is going to be 2 times the sine of 3 pi over 4. In quadrant 2, the sign is going to be positive, so this just comes out to the square root of 2. So we get our ordered pair is negative square root of 2, square root of 2. So really easy to go from polar to Cartesian. The other way is a bit more work, not too difficult. You just have to think about which quadrant. So let's go ahead and see how to do that. Let's convert 1, negative 1 from Cartesian to polar. So, well, the first thing is figuring out r squared. So r squared is 1 squared plus negative 1 squared. So r squared is 2, which makes r the square root of 2. Again, our r value is always going to be positive because the distance from the origin is always going to be 0 or positive. So you don't have to worry about plus and minus the square root of 2 there. So now we have to think about how to figure out what theta is. So we know the tangent of theta has to be negative 1 over 1, which is negative 1. And then think about what quadrant this point is in, right? We have 1, negative 1, so we're somewhere down here in quadrant 4. And if you're in quadrant 4, we know that the inverse tangent of negative 1 is going to be where the sine and cosine are equal, so that's again going to be pi over 4, but we're in quadrant 4, so we would say that that is 7 pi over 4. You could also do negative pi over 4, but those are just coterminal angles. So in this case, our theta is going to be 7 pi over 4. Again, if you do inverse tangent in your calculator, it's probably going to give you the value of 3 pi over 4, but because we know the Cartesian coordinates 1, negative 1 are in quadrant 4, that's how we know it has to be 7 pi over 4 and not 3 pi over 4. So in summary, our polar coordinates are r, square root of 2, and theta, 7 pi over 4. And that's it for converting. Pretty much all of them are going to work this way. Okay, so let's talk about some basic graphs. One nice thing about polar coordinates is some very simple equations produce some really interesting graphs that you don't see necessarily in rectangular, using rectangular coordinates. So let's look at some basic graphs. So again, our graphs are now going to involve the variables r and theta rather than x and y. So one thing that's really easy is, say, a circle centered at the origin. So if you have something like r equals 3, what would that be? That would just be the circle with radius 3 at all points, centered at the origin. So I'm not the world's best circle drawer, but you get the idea. So we get a circle centered at the origin with radius 3, whereas in rectangular coordinates, this would look like right, x squared plus y squared equals whatever the radius is. In this case, it's 3, so it would be the square root of 3 squared. So we get a much, or 3 squared. So no, the radius is 3, so it would be 9. So yeah, this would be x squared plus y squared equals 9 in the Cartesian coordinates, but here it's just r equals 3. So in general, r equals some positive constant is just going to give a circle with that radius value. So r equals k with k greater than or equal to 0 gives a circle. Centered at the origin. With radius k. Okay, what about if we let theta equal some constant value? What would that look like? So say we had theta equals, I don't know, what's a normal pi over 4, something like that. What would we get? Well, we're basically all points on the angle pi over 4. So we're actually going to get the same exact graph as if we did y equals x. So same thing here. If you let theta equal a constant, it's going to give you a line that passes through the origin. So theta equals some constant gives the line through the origin. Corresponding to that angle. Another interesting one, that's a pretty basic one. What if we took r and we let it just equal theta? So let's think about this graph. So r equals theta. What happens? Well, we're saying, okay, if r was equal to 0, that would just be at the very origin, and theta would have a 0 value as well. So we start out right in the middle. And then what happens? Well, as my angle tends to get larger, I'm going to be looping around, and I'm actually getting farther away too, because r will also be getting bigger. So what happens is we kind of get this spiral action. We see that we get farther and farther away, and we just keep twisting and twisting around. So this is actually what's known as the Spiral of Archimedes. And we see the graph twists around according to the angle as the angle gets larger and larger, and it also gets farther and farther away. So those are some of the basic graphs that we see. And there are a variety of others too. So we can give a quick summary of those. A lot of times it's useful to just kind of use a graphing utility to help these, because there is polar graph paper with a bunch of circles, kind of like Cartesian graph paper, but in practice it can be a little bit difficult to see some of these things. But why don't I go ahead and go through some of the basic examples, and we'll plot those curves on Desmos. Okay, so there's like three more classical examples of kind of basic curves. The first one we'll look at, these are known as Limisons. So they either take the form r equals a plus or minus some b times the sine of theta, or r equals a plus or minus b times the cosine of theta. So these are known as Limisons. I think there's an accent mark somewhere. I'm not exactly sure. But let's go ahead and just, a and b are constants that you can kind of play around with to change the shape, and we'll get an idea of what those look like. So if you're on Desmos, we can, I don't know if we have to switch to polar. I think we can just type r equals, let's say 1 plus 2 cosine of theta. Yeah, and we get a limison. So that's what it looks like if you have the cosine. What about if you have the sine? You get something like that. So similar thing, just rotated. It looks like 90 degrees counterclockwise. And again, you have the number of periods here that you can graph it for. Since it's sine, it's periodic. It'll just keep looping and going through that same pattern again and again. Let's go ahead and maybe put a minus in there. Notice that, again, that's just a rotation. So what if they're both negative? Yeah, so you get the idea of that basic shape. Some of them don't have the loops in them. Yeah, so you see one like that just has the, it comes to a cusp, depending on whether or not the constants, how they compare in sizes. So if it's larger, I believe we're going to get something that looks a little more round. When you have the constant being multiplied with the sine or the cosine, you're going to get that loop on the inside. So that's the basic shape of the Limisons. So let's go back and let's talk about the next shape, which are going to be the rose curves. So 5, we have the rose curves. So the rose curves are basically r equals, say, a sine of n theta, or r equals a times the cosine of n theta. So that n, whether it's an even or odd number, typically it's an integer, is going to tell us how many rose petals we have. So let's go back and look at some examples of this on Desmos. So maybe we have 3 times the cosine of, let's say, 3 theta. So notice this has 3 petals, and the sine will also have 3 petals. So when the coefficient on the inside is odd, you're going to get exactly the number of petals as that number. When it's even, it's going to be doubled. So if I put a 2 here, I should have 4 petals. And same with the cosine. So you see those rose curves. The number on the inside is going to affect the number of petals, and the number on the outside is just going to affect the size of the rose petals, how big they are. And then the last type of curve we want to talk about is the Lemnas Gate. So the equation for the Lemnas Gate is a little more complicated, but basically what it's going to give you is a figure 8 or an infinity symbol. That's what it looks like. So this equation looks like r squared equals a squared times the sine of 2 theta, or r squared equals a squared times the cosine of 2 theta. And again, these are known as the Lemnas Gates. So this is a Lemnas Gate. So let's go ahead and take a look at that picture. I've kind of already previewed what it's going to look like. So I don't know, let's say we have 4 times the, so we need r squared on the side. 4 times the cosine of 2 theta. Oh, it doesn't want to let me, polar equations must be linear in R. So what I'm going to have to do is I'm going to have to do 2 equations. I'm going to have to do both halves. So I'll do the square root of both sides. I'll have to do plus and minus. So 4 cosine 2 theta. So there we go. We actually get the full Lemnas Gate there. So if we did minus, it shouldn't add anything. That would give the other half, but it still gives the same picture here. And if we change just the sign, we should get the same shape, but we see now that the Lemnas Gate itself has been rotated pi/4 radians counterclockwise. Anyhow, so those are all the basic shapes you see. You can always play around with these things to see if you get something more interesting. There's lots of different curves that arise from this, but those are the basic ones that come up. And again, this is kind of just like a refresher if you hadn't had any polar coordinates in pre-calculus. So that's it for this section. This is Dr. Lennon signing off.